Hello, everyone, and welcome to our webinar series. So today we're going to go through the second episode of unveiling the 1.0 for Zenoh. And I'll be sharing my screen in a moment and we'll get going. So first of all, thank you to the feedback that we had concerning the first episode. I see lots of excitement and many people which very much enjoyed the webinar. Obviously, that's always positive feedback for us. We put all of our effort and passion into this, so it's always good to hear that you enjoyed. But enough talking. Let's get into the second episode of this series. And so, real quick recap for those of you that missed the launching webinar, and then we'll dive into a few of the new features or updated feature of 1.1. So first of all, important to recall that with 1.0 comes a series of guarantees. Well, first of all, wire interoperability, okay, between version 1.x.star and no API break across, let's say, version 1.star.star. In addition, as a consequence of Eclipse project release, because obviously V1 will also be an Eclipse project release as it was V011, you have the guarantee of an IP license and patent review. So that's, I think, quite important guarantee with respect to the safety of using Zenoh. Now, what's new in 1.0? Real quickly, as we covered last week, we made quite a bit of work in terms of ensuring consistency and coverage between API. We ended up building some tools ourselves, actually, to make sure that we can automatically check the coverage of API across the zillion of language bindings that you have. I mean, imagine for a moment making sure that you have exactly the same API coverage in C, C++, Rust, Python, Kotlin, Java, as we will see Typescript, and so on and so forth. And if the API, it's more than 10 calls, right? That's quite some work to do manually. So we actually even had to build some tools internally to support this. But the good news is that the deviation will now, to some extent, automatically detected. And in any case, we have, an automated way of spotting what are the gap and if there are inconsistencies. Now, obviously, that led also to harmonization, and as I mentioned before, and we'll get a sneak peek today, support for TypeScript. So finally, you will get to see how the TypeScript API looks like. Some improvement on the protocol, and in fact, if you recall, when we started announcing the 1.0 at the last Zenoh user meeting, December 2023, we had mentioned that there were few protocol changes that we wanted to roll before v1.0, and we have completed those all. They were rolled in the last 3 releases. And I think that's quite important. We described some of those extensions last time, but those allow us to further improve the scalability of Zenoh and the control that you have as a programmer, as an architect, to decide what is important to your application with respect to either having precise information about discovery or improving scalability, especially for very constrained device. In any case, we covered this last time. I'm pretty sure we will have zoom in later on in the year. And this is what we call intents, okay? And the release blog will provide some additional coverage. Some improvement of scheduling, as we mentioned last time. Please, if you want to learn more about it, refer to the previous episode in this series. But improvement of scheduling, especially as a consequence of moving from async to Tokyo. There were some scheduling changes that were creating some issues in some scenarios, and all of those have been addressed. So we moved in Tokyo pre-011, okay, because it was a huge changes. We didn't want to delay that to 1.0. But we have completed the transition to Tokyo by upgrading all of our plugins also to use Tokyo. As you might know, for those of you that come from the Rust world, async is able actually to run Tokyo futures. Okay, can behave as there is a Tokyo compatibility mode. That was the mode that was used in 0.11 because we had a Tokyo in the core of our framework, and then async still in the plugins. And something we'll discuss in depth today, a new shared memory and zero copy framework. But again, I don't want to spend much time covering the summary because this will be one of the subjects that we'll be covering in today's webinar. Access control, which is something else we'll cover in today's webinar because we have never given the detail of this, and RMW we already covered last time, as well as the tools that are coming with respect to improvement in the ZettaScale provided platform as a service that allows you to provision, deploy, manage, and monitor Zenoh router in a public infrastructure, in a public cloud, and in general in the continuum from this cloud down to your favorite device. Support for ROS2, so you will be able to visualize the ROS graph. You will be able to visualize, obviously, ROS nodes that belongs to the ROS graph as a list, and the list of action and services. Support for DDS, because again, you might want, or might still have, some DDS in your system, and so you will be able to discover ROS. By the way, for those of you that are not in robotic, ROS is the most widely used robotic frameworks, and historically was using DDS as a communication protocol. So you will be able to map, in fact, ROS entities to DDS entities, and that will, I think, make it quite easy for you to debug your systems, and do this if you're running Zenoh outside of your robot, essentially from anywhere on the internet. Version of this tool will also be available offline, as we'll demonstrate toward the tail of this year. Okay, now let's move to the first topic of today's webinar, which is shared memory and zero copy. And this is very important. We have had support for a long time in Zenoh, and it's funny because actually few people notice that, okay? Because I think many people don't expect a protocol like Zenoh to support natively that kind of use case. So let's start to review what was available in Zenoh up to 1.0, and let's try to understand why we decided to expand and extend what we had there. So as I was mentioning, Zenoh had support for zero copy and shared memory since version 0.60, which is a couple of years old. The entire shared memory support is written in Rust, and it is completely decentralized. This is a big difference with respect to many of the other frameworks, where usually you have a centralized daemon that manages the shared memory. In Zenoh, there isn't such a centralized things because it just doesn't match with Zenoh modus operandi, introduces single point of failure, and also, in our experience, makes it hard to dimension your system, okay? It makes it hard to build systems that are evolvable, because all of a sudden, right, imagine I have a system running with a shared memory segment that was dimensioned for the system at the time t. Now, especially if I have a microservice architecture, I need to deploy a few new microservices, but perhaps, right, the shared memory wasn't configured to account for those. So I have to shut everything down, and usually with existing technology, restart the entire system in order to do this incremental update. With Zenoh, that wouldn't already happen because each process owns its own shared memory, as we will see. Now, which were some of the assumptions? Well, first of all, one of the goals of Zenoh obviously was decentralization. The other one, as we have always aimed for, was safety and ease of use. So for the Rust implementation, we had integrated shared memory support with the Rust type system, and essentially we were leveraging the borrowing system and ownership to do garbage collection, okay? And in fact, it's a distributed garbage collection problem. Now, we had put on ourselves one topological restriction because it was just making it a little bit easier, which was we assume, okay, that in order to leverage our shared memory framework, your application, your peers are communicating over a click. So why did we put that limitation? Because our previous garbage collection mechanism was assuming, right, or consider the assumption that as far as I've shared the shared memory segment with you, and as far as you are not able to further route it, okay, because you know that in Zenoh we can mesh route things, then in this case, I can have a series of assumptions on the use of this buffer, which is tied to the liveliness of the session. Okay. Now, as soon as I allow application to route application or routers, because you know that peers as well as router can route data in Zenoh, to route shared memory buffer. And again, when you think router, don't think necessarily of a car. In a multi-domain application, I might have multiple domain that communicate between them through routers, even if we are in the same system on chip. And between domains, maybe I will want to do some shared memory. Okay. So we started to see these use cases, and as soon as you let data to be routed, you cannot bound anymore the availability or the use of a buffer to the liveliness of a session, because perhaps I have no session established with someone that is 3, 2, 4, God's know how many hop away, and using my shared memory buffer. So that would require us to change our memory garbage collection, distributed garbage collection strategy, which is something we did. But that wasn't the only things that we wanted to extend. Something else that actually, from people that actually found out that Zenoh had native support for share memory and started using it, they said, well, great, you have support for POSIX share memory, but what if I have some hardware and I want to allocate memory out of this hardware? How can I do that? And actually, we couldn't in the pre-1.0 share memory implementation. So just to articulate why we need more and to visualize some use cases, if we refer to topology, one of the most trivial, topology that you can think about, and you find this in plenty of systems, from data processing that you might find in a radar to processing pipeline that you might have in control system, robotics, cars. And a pipeline is just the simplest form of a processing graph, because if you look at, for instance, ROS graph, they tend to be far more articulated. But the basic idea is that if I have such a pipeline, sometimes I want to be able to compute through this pipeline while sharing this same buffer, so with zero copy and shared memory. And you see that if we were to be able to support this, all of a sudden, a buffer that might have been allocated in the shared memory managed by process P1 would end up with a reference from process P3, with which potentially we didn't have a session. And so, this wouldn't work. It was not the case supported in pre-1.0. It's supported in V1.0. So once again, this is the simplest case. You can think like an image processing pipeline. You can be very creative, and all of a sudden, you have a super efficient way of processing data through the stages with zero copy end to end, which is quite cool. Okay, the second example is, sometimes you have special hardware because maybe you have a system on chip with a processor and a microcontroller, and there are certain region of memory that you can use to communicate between efficiently communicate between the microprocessor and the microcontroller. It's true that sometimes vendor provides you actually with Unix socket or TCP/IP stack implementation that are built on top of that shared memory, but that's kind of a pity, right? Because we are communicating between two microprocessor inside the same system of chip using TCP/IP. Kind of crazy. While actually under the hood, there is a shared memory area that we could use to communicate. And wouldn't it be great if we could actually expose it to Zenoh to go allocate and then communicate efficiently through the shared memory region? That was something we wanted to do. Another use case is I really want to have true zero copy. I have a region of memory in which that is filled by DMA, it's filled by camera, by a graphic card, whatever. And I don't want to to copy that data into another buffer before sharing it with other processes, because if it's a huge image, right, that takes time, that takes CPU. And so once again, the need of being able to support arbitrary shared memory provider in a system that can really, I think, be probably the most flexible I've seen so far in terms of COTS system supporting what Zenoh supports in combination with shared memory and making that completely transparent, as we will see with respect to the API. Another point is buffer overflow and underflow protection. So all of our API is safe in the sense that if you try to under or overwrite, that will be caught actually in Rust, C++, to some extent in C. Then depending on your programming language, either a programming mistake or someone malicious could still overwrite. And for some safety critical application, it is very important to detect this override. This is why usually if you allocate a shared memory buffer, you would want to have canaries before and after in order to detect potential overrides and as a consequence, reason about the integrity of this buffer. And this is something that now we also can support with the new shared memory subsystem. Okay, so enough with introduction. Let's see what the new shared memory subsystem brings you. First and foremost, no topological constraint. Okay, so there are no more topological constraints in how you can use shared memory. So it can be an arbitrary graph as far as the sender and the recipient are in the same shared memory domain, okay, and they support the same shared memory providers, you will receive shared memory, okay, which is quite nice. And what this means in terms of the shared memory provider, you will understand in a couple of slides. We have now a distributed memory management still, so no centralization, that was no option for us. Safe mutability. This is something that we didn't have in the previous version of the shared memory. So for those of you that have used shared memory, essentially, when you will allocate a buffer, this buffer from the shared memory allocator, this buffer used to be immutable. And there was an unsafe operation to make it mute, where the documentation was saying, it is your responsibility to ensure that you are the only one who has mutable access to this buffer, okay? So we were kind of pushing the problem to the application developer. The big news of 1.0 is that actually you can check if you are the only one who has a reference and safely transform a reference into a mutable reference, which is great. Okay, you can even wait to become the one or the only one that has a reference to then eventually mutate the buffer. So we think this will be great improvement in the way in which you can build application, or the ease with which you can build application, and more importantly, will lead to building more easily correct application. Okay, because all of a sudden you're not the only one with a reference, with a live reference. There is no way you can turn that reference into a mutable reference unless, again, you go through unsafe. Okay, because maybe you say, okay, I know exactly what I'm doing. You get into unsafe land. In that case, you are the boss. Okay, we decline our responsibilities. Shared memory providers have been introduced. We by default, we provide an implementation for POSIX shared memory provider. In the example, as we will see, we show how simple it is to implement a shared memory provider. We have at least 2 customers that have already implemented shared memory providers, and the feedback is that it's a piece of cake. And that has a huge flexibility, because all of a sudden you decide from where you're going to pick your shared memory. Custom layouts, and in fact alignment. So I think that's quite important and goes back to the concept, for instance, of canaries. You can implement canaries by just using custom layouts. And once again, this induces minimal system and network overhead for both normal and failover operation. Okay, so what you will notice is that actually you won't see any traffic, essentially any traffic added on the network because of the distributed garbage collection. okay, which is quite nice. And we've done some evaluation on the additional CPU utilization, and it's on modern hardware essentially negligible, okay? Okay, so let's look now at the high-level architecture of the Zenoh shared memory subsystem. So essentially, as we will see in the coding lab, what you will do now is to pick and decide which backend you want to use. Might be a backend that we provide as a built-in backend, or might be a backend that you have built. Okay, so nice, because you can, as I mentioned before, you can write a backend for a GPU, or for some custom hardware, whatever. Once you decide the backend that you want to use, then you instantiate, as you see in this code, a shared memory provider with the proper backend, and you assign a protocol ID to your shared memory. What is the role of this protocol ID? So in Zenoh, an application could use as many shared memory provider as it wishes. And each memory provider could be using a different shared memory backend. And so the question is, when you receive data from me, okay, well, or how do you know how to get access to that specific buffer? You need to know the ID of the shared memory, and that's precisely the protocol ID, which we predefine for the shared memory that we support built in off the shelf. But whenever you add a new shared memory, you can define your own protocol ID. Okay, that's quite important. Okay, and once you have a provider, then you can just do provider.alloc, and that will return you a buffer. And as we will see, this buffer has nothing special with respect to how you or what you need to do in order to use it in the context of a Zenoh API. You can use it like any other buffer, okay? With the difference that Zenoh does the magic that we'll describe next. Okay, now if you want to specify a layout, what you can do, you can take a provider, right? You define an allocator for a given size. You define, for instance, the alignment. You transform this into a layout object, which is like a blueprint for the kind of buffer you want to allocate. And then you just do layout alloc, and that allocates a buffer for you, okay? Which is quite nice. You can pass this even around if you're using a sync to different tasks, so they can allocate with the right layout, with the right size, without knowing what is the layout, what is the size. And that can come potentially from a single place that it's much easier to manage in your code, in your system. Garbage collection and defragmentation. So the principle that we follow in Zenoh, and that is the same as in 0x, okay, is that we are lazy, okay? In which sense? We are lazy in the sense that we keep track of what is alive, what is not alive. But as there are people that build the real-time system, we don't want to run garbage collection under the hood, okay? And so we give you the choice of when running garbage collection. So you can call garbage collection depending on your application. Periodically, you can call it in specific task, or you can cause, as we will see, an allocation to cause garbage collection. And again, garbage collection, don't think of Java and having to track all the routes. I mean, for us, garbage collection is just scanning the our allocation list, see what has been freed, and what has been freed, move it to the free list. Okay, that's the allocation. So usually it's very fast. It's like going through a linked list. You should visualize it like this. Okay, so the complexity is linear in the length, okay, of the buffer you have located so far. But yeah, that's kind of still an operation that is pretty fast. Now, obviously, what might happen, okay, depending on how you use share memory, is that you have an allocation and the allocation pattern, and all of a sudden your memory gets fragmented. So I might have lots of shared memory buffer that used to be filled that now they are empty, and but their size is smaller, okay, individual size of a buffer that I'm trying to allocate now. And so in this case, what I would have to do, I would need to defragment. So all of a sudden, coalesce contiguous buffer that are free into as big as possible buffer. And that's what we call the fragmentation. What has always been the fragmentation, even in previous version. And again, you can control the fragmentation manually, or and so call it whenever it makes sense for your application, or you can trigger it, as we see here, as a policy when trying to allocate. So let's look at the code for a moment. Here you have two examples. When we try to allocate the A buff, okay, what we do, we allocate with a policy that says, please block on defragment and garbage collect, okay, which says, so if you cannot allocate a buffer, then try to defragment, because there might be, and it's just a matter of coalescing buffers in the free list that are adjacent in address, okay? And still, if that doesn't succeed, please do a garbage collection, okay? And if you turn that around, that will work the other way around. And unless, and you will wait for all of this, okay? And by the way, you can wait synchronously or wait through await, so in the future. So do asynchronous programming also with our allocators, just because there are these potentially consuming tasks, to some extent consuming tasks that you might need to undertake. You can also say, look, deallocate 1000, okay, the first 1000 slot, and if you can allocate, return immediately. Otherwise, do a full garbage collection and defragmentation. This is interesting because it allows you to bound the amount of time that you might spend, okay? And you could even bound, right? I want to fail if you cannot find a slot that suits me in the first 100 slots, okay? So there are lots of policies. Just look at documentation, but the system, it's super powerful. Okay. As I was mentioning before, when you get a shared memory buffer, you can use it like any other buffer, and it's Zenoh that does the magic. So as we will see, you can use it on a put, you can use it as an attachment of a put, you can use it as a reply of a query, you can use it as a query payload, okay? And what under the hood, what happens is that it is our Zenoh runtime that decides when it sees this buffer, says, okay, so this buffer has to be received, by A, B, and C. So A and B happen to be in the same shared memory domain, because when opening a session, we did negotiation, and I know that we are in the same shared memory domain. So in this case, I'm going to use through Zenoh just a shared memory protocol to communicate some super tiny information how to get it. So few tens of bytes communicated and done. Okay. If C happens to be across the network, or perhaps not within the same shared memory domain, okay, then in that case, Zenoh will actually send the full data on the wire. And by the way, sometimes perhaps you do not want shared memory to be sent outside of a boundary represented by P of a node, and that can also be configured. There are use cases for that too, which we don't have the time to discuss now. Okay, so on the sending side, it's completely transparent, right? Well, the only thing that is not transparent is the act of allocating a buffer. And why? So if we go back here, why did we make it not transparent? Well, because that's the only way to have true zero copy, right? I mean, through buffer provider, you could actually grab a buffer in an area where that has been filled by DMA or a graphic card, and literally put into Zenoh. And on the other hand, you have exactly the same buffer. It's very hard to do better than that, okay? If we put it under the hood, then all of a sudden you would have maybe, right, the buffer that then we would have to copy in another buffer. And so you would have at best only one copy if you try to hide the allocation. So we think that it makes sense because it makes the system far more flexible there are already users that we are doing of this approach that are quite useful in that Zenoh RMW. And so this is why we provide you allocators. And then, with, various asterisks of warning. If you really want to get wild, right, there will be probably C++ programmer here. I don't know of much of you have ever built some memory subsystem or some memory manager in C++, but the placement new, right? All of a sudden, and again, with all needed attention, but you could use placement new over such a buffer. That means that I could allocate in C++ types on the shared memory buffer and have the exact types on the other side. Why do I say with lots of asterisk and lots of attention and disclaimer? Because in this case, you need to make sure, right, that who receives this has exactly a programming language that exposes the same layouts, right? Those who have to understand understood, and I'll pause there. But you kind of get the wild things that you can do and that eventually will be able to do building on top of this first step. Okay, so getting back, I think I covered everything in this side. So we discussed the publisher. On the subscriber side, it's completely transparent. You don't need to know unless you want to know. So let's look now at some code. Okay, maybe I should increase a little bit the font. I should have increased that before. Or maybe, is it sufficiently readable? Because otherwise we won't be able to fit much code in it. So I'll go full screen, and I think that should be sufficiently readable because it's readable for me, and I don't have a very big screen. Okay, so let's start with the publisher. Okay, so let's go on the code that is kind of, oops, that's what I want, pub for share memory. Okay, so as we see here, well, we open a session, nothing new there. We pick our backend, okay, as we discussed in the slides. In this case, we are using a POSIX share memory provider backend. But again, you could have your custom backend. Once we have a backend, we can build a provider on top of the backend. And the nice things that, just to understand, as you will see when I show you how to build a backend is trivial code because all the logic on how to manage and do the garbage collection and everything else is on the provider. And you get that for free because we've implemented it, okay? So once we have a backend, again, built-in or bring your own backend, we can create a provider with, again, the protocol ideas we saw before in the proper backend. Here we are declaring a publisher, so nothing new there. We are creating a layout allocator. And by the way, in here, we are locating the share memory buffer, okay? And notice that we are using the synchronous API. So this future will be ready as soon as our allocator manages to allocate a buffer, okay? And that might be immediately or after having done garbage collection. But in this case, it doesn't do fragmentation, okay? Because there is no fragmentation policy. And then, there is just some feeling, but the important line is this, right? So we are putting a shared memory buffer into a put like we would do with any other buffer. And in fact, if we look at this line versus what we have in the publisher, right, where we are putting a buffer, and the buffer actually happens to be a string, okay, you see that nothing really changes, okay? So in terms of programmer, for you, it's quite transparent. And as I was mentioned before, this will work with a regular subscriber, no problem. So let's just take a look at it. So if I start a regular subscriber here, and the publisher for share memory, then you see that it received memory. It received samples. But by the way, these are received through share memory buffer. The subscriber has no clue that these are share memory buffers. Okay? But that's share memory. So there is no copy involved. but for the subscriber receives a sample, the payload exposes a buffer. This buffer happens to be a shared memory buffer. You don't need to know unless that matters to you, okay? And if it matters to you, then you can actually check for it. And if you look at the example Z sub shared memory, you see that here it prints a shared memory that wasn't printed before. What is that about? Let's go and take a look in the code. So if we look at the subscriber shared memory, which is here, you will see that what it does, it prints a payload type, okay? And the payload type in this case is shared memory. So if you have a subscriber that needs to know when it's receiving something on shared memory, you have a way of understanding it and dealing with it if you need to deal specifically. Voila. Okay, so the other things I want to show is a shared memory provider, just to show how trivial it is to make a provider. And this is not a joke, that's all it takes, because all the intelligence is in the is not in the backend, is on the actual provider. So this is implementing essentially the a backend, okay? And no, there are just a few traits that you have to implement, few properties to define, and essentially you are in business, okay? Okay, so let's get back to our slides. And let's start looking at interceptor frameworks. So there are lots of problems that in the end boil down to you being able to inject rules into the routing path, okay? So for a moment, think about deciding what's get in or what get out of anything, right? Think about downsampling. And there might be plenty of other cases in which I want to inject logic into the routing that happen either ingress or egress. And this is why we introduce in Zenoh a routing interceptors and two examples that we provide as feature, right, that can leverage this framework are downsampling and access control. Let's start with downsampling. So today, if you look at the default configuration, there is an example of downsampling. But in general, it is sufficient to add a downsampling declaration in which you define the interface on which you want to downsample, the flow. So is it data outgoing or going out of that interface, so egress, or is it ingress, so data incoming from this interface? And then the rules. So in this case, for instance, what we are saying is that, look, anything that gets out of the wireless LAN 0 for key demo example Zenoh RS pub, downsample to a frequency of 0.1 hertz. Okay, that's as simple as that. The rest is done by Zenoh. So when would you use these kind of things? Let me give you an example that actually in which this is used quite often. Imagine you have a robot, you have a car, a subsystem. I mean, there are whatever that is, in which you find yourself having high frequency data that needs to be distributed at that high frequency without the boundaries of your devices. That be the robot, that be the car, a subsystem, a ship, a car, whatever. But the same data doesn't need to be shared with the rest of the world, or in some instances cannot, for security reason, and I'll get back to that, shared with the rest of the world at the same frequency. Okay, I need to downsample the data. Well, that's a super common requirement, and Zenoh now support it natively. Just declare downsampling for the key expression on which interface, ingress, egress, you are on business. So getting back to the temporal limitation, for instance, in the stock market, okay, there is certain data that is provided to financial operator at a much higher frequency that can be provided to third party. Okay, so that's just one example. And there are plenty of other applications where data is relatively, well, the temporal accuracy of data or the freshness of data is, or the granularity with which you receive the data, it's so important that you need to downsample what you provide. And in this case, you have just built-in support in Zenoh. Second example of applying interceptor is security, and more precisely, access control. Okay, but before getting access control, quick reminder of what Zenoh support in terms of authentication. So in Zenoh, you can enable authentication, and there are roughly two ways of doing authentication. You can do authentication based on a secure transport that would be using TLS or MTLS if you want mutual authentication, or either quick, which again can have symmetric or asymmetric authentication. The other approach is to also enable our authentication plugin. And as of today, again, you could develop your own, but we provide just user and password as an example. Okay. So for instance, I could have, in one case, I could have asymmetric TLS or asymmetric a quick authentication. And on top of this, now I've authenticated the other party, right? And I could do user ID and password, for instance, or I could do symmetric authentication in that, or mutual authentication. In that case, I don't need user ID and password. This is what Zenoh support. There are references where you can learn more about this, and this concerns the authentication. Now, how about the access control? Now, in Zenoh, the access control allow us to essentially give rights to subject with respect to the operation they can perform on core, I would say, Zenoh primitives, okay? Such as producing, consuming data, querying, or replying. Okay? And that's essentially the key idea behind Zenoh access control. And then, sorry, we use these rules to filter message based on their characteristics, the source, and the destinations. This can be configured, in fact, is configured as part of the Zenoh configuration, and we'll show this. But in general, if you see this example deployment, we have two routers. And in these two routers, for instance, we want a put from the device here on the top left to be received by the subscriber on the bottom left, but actually not to get anywhere else. Okay, that can be done easily with Zenoh access control, and I can control that usually, as usual, using key expression. Okay, I could do the same here. So in this case, I have sensor temp that is received in the subsystems, but it's never transmitted across the system or across the boundaries of this router. Access control rules can be applied to routers, they can be applied to peers, they can be applied to client. Okay, so in that respect, there are no limitation here applied to routers, just as an example. Now, in terms of rules, this is how they are structured. So if you want to enable access control, then you have to say, yeah, I'm enabling it, and you have to list the rules. Rule have an ID, a permission, which could be allow, deny, a list of messages. Okay, are you allowing put, delete, declare for subscriber or for queryable, query, or apply? Okay, because perhaps, for instance, maybe I don't want the declare subscriber getting out of a given boundaries, or I don't want to declare that anybody in the rest of the system knows the queryable I'm exposing. So I am actually able to control who can see my declare queryable, for instance. Okay, likewise my replies. Then I can control the flow, egress or ingress or egress, and the key expression. Okay, so this is how a basic rules would look like. So in this case, in fact, we are allowing everything, right? Because we're saying, in fact, the rule is called allow all because the permission is allow. The messages are all the messages on which you can predicate. The flows are egress and egress, and the keys are star star. So we're actually allowing everything. Okay. Now, what are the subjects that you can use for access control. So a subject can be an interface. Okay, so I can say, well, through this interface, in egress, that's what is allowed, and egress, that's what is allowed. It can be an identity, meaning a certificate identity. Okay. Um, or a combination of two, or it can be, none of those. So here we have another example of an access control rule in which you see how we can associate rules to subject. So in this case, it's a deny, where we allow all, but we allow all only for car or phone, where these are identities that have associated certificates. Okay. So the only things that happens is that nothing, so everything is denied by default because that's the default permission. And then we are just allowing everything for identity car or phone, which means the car and the phone will receive anything that is published, but the robot won't receive anything. Okay. So here I have an example of a config file. This can be quite articulated, but we will be providing as ZettaScale tools that facilitate the configuration of these files. And I drink because I have a little bit of a cold. So talking, it's a little bit tough. Okay, let's move to TypeScript. So as announced, we will be releasing, for what concerns TypeScript, will be alpha release. Okay. And here you have a snip of a publisher. So in terms of code, it looks quite familiar if you are familiar with Zenoh. So again, you open a session, you can use WebSocket or Secure WebSocket. Both of those are supported. And then you just declare a publisher and put the buffer on and execute the put operation. So that's pretty straightforward. You have a link to the repository. By the way, there is a typo here because it was supposed to be a string. I will simplify the example. I zapped the buffer, but I forgot to replace the buff with the string. But anyway, that's how it should look like. And in this case, you can have a router or a peer where you activate the TypeScript plugin. And in this case, application written in TypeScript or JavaScript, web-based or whatever, Node.js, they can just get access to the full power of Zenoh from TypeScript or JavaScript. You have a reference to the repository. Feel free to give us feedback. Okay, serialization. So this is something else that it's misunderstood in Zenoh. And this is the last topic for the day. And I want to repeat once again that Zenoh does not impose any serialization framework. So you can use whatever you want. You can use protobuf, flatbuf, CDR, whatever. Okay. Zenoh provides you a mechanism to associate encodings, and we define a series of encoding that cover most of the commonly used encodings for data and for use by serialization format. But you can define your own, and I think that's important. That said, what Zenoh does to make your life easier when in embedded systems, because if you're on Arduino, do you want to pull in a protobuf dependency? Well, perhaps not. I don't even know if there is protobuf for Arduino. Probably there isn't, but perhaps you don't want to pull it on. If you are certifying your system, usually there is a complexity in certifying the serialization framework. Or if you're just writing a simple application, why you should be bothered with pulling in a serialization framework? So to support these use cases, what Zenoh provides across all supported programming languages is the built-in support for serializing and deserializing primitive and core container types. Okay, so again, I'll repeat. Zenoh doesn't constrain you, right? You can use whatever you want. On top of that, to address the case that I just mentioned, embedded system that don't want to add external dependencies, certification for which the external dependencies, or the more code you need to certify, the more complex is the impact. Or very simple application, we provide built-in they get you quite far, but are not intended to replace protobuf or CDR or whatever. Okay, I mean, you could use that as building block to implement a full-blown serialization system. That's not our intent. Okay, so let's see how this looks like, because we have added in 1.0 an example that shows precisely how this works, so that you can use it once again as Rosetta Stone, because by now you have understood that our example are intended to be a way of learning the API, and a Rosetta Stone that you can use, or Rosetta code as a project you can use to compare how you would do the same things in different programming language for the various API that we support. So, for instance, right, if you take an U32, okay, you can serialize it, and in fact, the Z byte from in Rust just serialize it, okay, and you get a payload, a Z bytes, and the deserialize gets you back the U32, and these are the assert. Make sure that obviously that works right, okay. So we can deal. This is why you can put integer in Zenoh, because under the hood we know how to serialize it, and that makes your application much easier, because for you it's transparent. We know how to deal with it, and for many simple application you get by batteries included. Same things for a string, right? So you can do the from and then the deserialize. Let's look at some more juicy type, a vector. Okay, so here I have a vector of U8. In fact, that would be true for vector of any primitive type that is supported. I can now serialize by using from, and again deserialize, in this case using nin2. Okay, so likewise, well, that's a cow vector. It's also supported, but let's get down, because I will let you scroll for arrays. But let's look for hash map, which is also interesting, right? So all of a sudden you can have an hash map that you can fill, and then eventually you can serialize it with the from, and then you can deserialize it again with the payload deserialize command. And if you had JSON, okay, once again, in this case, you could serialize it using, you can create a JSON object, right? Serialize it as a JSON object and deserialize it as a per JSON object, okay? So this is a string. You don't even know if this is valid JSON. This makes sure that that's a valid JSON object, okay? And what you're seeing on this line, that we are able to serialize essentially a JSON object and also deserialize it back. YAML, okay? So here you have a YAML data type. Likewise, we are able to serialize YAML and deserialize YAML. Okay, that's quite nice too, because it's a very commonly type used for configuration. That's built-in support. Protobuf, okay? So in this case, in protobuf, you would be using an external serialization mechanism. So in this case, there is the framework uses Prost, which is the standard in Rust. We are defining an entity info, okay, with an integer and a string, initializing the entity. And then in this case, this is actually the serialization that is done in Serde. We are transforming into Z bytes, right? And then you just deserialize through Serde, okay? Because you get the payload back and deserialize through the Serde decode. So that shows that you can plug easily also an external serialization framework. And again, you have this Z byte example also for C, C++, Python, and so on and so forth. So once again, that is your Rosetta code. Okay, so as we mentioned last time, we are into the release countdown mode. We're releasing a beta version of Zenoh per week until the end of the month. This week we should have the first release candidate. We should be essentially on track for that. But again, usually we have a checkup at the beginning of the week, and then on Thursday, and then we decide if we're, where we stand. And in any case, there will be a release on Friday. We'll decide if it's a release candidate or a beta. We should be on track, modulo surprises. As I mentioned last time, the passenger tools will be released 2 weeks after the release of Zenoh. And once again, I would like to thank all the community members, because you've been very supporting, helping us, finding bugs, giving feedback on the API, lots of constructive critiques. That's the way we like it. So thank you for your support. Please, keep up with it, because that's great for us. And that was my last slide. So thank you very much. We'll move now to Q&A. So let me actually stop sharing my screen. Okay, and let's see if there are any questions. Just give me one moment to go on the chat. Okay, so first question, is there any Go support? That's planned for post V1. Okay, so and in fact, we are planning for post V1 Go and Swift support. Okay, so let me go back to other messages. Okay, there is another question asking if providers, shared memory provider, are dynamically loaded. Well, they implement the trait, right? So shared memory provider backend, that's really the question. Shared memory provider backend implement the traits, and you have to pass an instance to a shared memory provider. How you get it, it's your problem. So if you want to load it from a DLL or a library, you're welcome to do that. We just provide you a traits, and we provide built-in providers, okay, or providers backend. So yeah, nothing would stop you from doing that. Okay, let me check if we have some more questions. Okay, I think that's it. So, well, thank you for attending, and I'll see you next week. Take care. Bye, everyone.